Let's begin video 4. I might be able to get through everything remaining, which is mostly just naming alkenes, alkynes, and alkanes. We'll see how it goes here. I'm trying to limit these to about 30-minute segments, so you have a lot of videos to watch, but just take your time. And again, this is at least a week and a half's worth of, probably 4 lectures worth. So again, I was talking about this special type of isomer called geometric isomers that exists between cis and trans isomers. So let's just go back and continue this discussion. As I said, these are different compounds because you cannot rotate around that double bond. So these two methyl groups are stuck on the same side, which we call cis. These two methyl groups are stuck on the opposite sides, so they're called a trans relationship on opposite sides. So we have to come up with unique names. You'll notice that each compound has a unique name. So each of these compounds has 4 carbons in a row, so they're both based on butane. However, they have a double bond, so we change the ane ending of butane to butene for an alkene, a double bond containing compound. And we got to do one more thing. We have to tell you where the double bond is in the chain, in the longest chain. In this case, it doesn't matter if you start from here and number or here and number this way. You get the second position. At the second carbon, the double bond begins. At the second carbon, the double bond begins. Either whether you number this 1, 2, 3, 4 or this 1, 2, 3, 4. It's the same thing, 2-butene. Notice the dash between the number and the letter. And then one more thing, to make it totally complete, you add the prefix cis onto this 2-butene, and this one you add trans to indicate that this molecule here on the left has the 2 methyl groups on the same side. This one has the methyl groups on opposite sides. So let's try some more examples to get you some more practice with that, because that's what organic chemistry is, a lot of rehearsal, a lot of practice. Let's go over some cis-trans examples. So I'll use line angle drawings and structural formulas either way. They're both useful for drawing these things. So here's our cis and trans 2-butene written as line angle drawings. Notice in the line angle drawing you only draw the carbon framework. CH3, CH, CH, CH3. Here we have CH3, CH, CH, CH3. Opposite sides, same side. What if we draw a compound like this? This is a different molecule. It's also 4 carbons in a row, but notice it's something slightly different about this one. On one side of the double bond, it's got 2 identical groups, 2 hydrogens. So let me draw it out like this. Instead of drawing it like this, I'll draw it like this. CH3, CH2, and then I'll draw the the double bond here. So there's this carbon, and then with the hydrogen attached, and then the double bond, and then the carbon with 2 hydrogens attached. You cannot have cis-trans isomers with this molecule because you need to have 2 different groups attached to this side of the double bond. You have 2 identical groups, so it doesn't matter if this is here and this is here, or this is here or here. It's the same molecule, so there's no cis-trans isomers. You would just call this molecule, would actually be named 1-butene, because it's 4 carbons long, so it gives that prefix. It's an alkene, so you give it that suffix, the ene, but you also got to tell us where the double bond is. It starts at the first carbon. That's what that number 1 means, the 1 dash. Try this one. Look at this one. It's not immediately obvious if it can have cis-trans isomers, but if you draw it out like this, you can see that it can have them. So let's just follow my finger along in the pen. So here's CH3, CH2. Now here's the first carbon of the double bond, this carbon here, with its hydrogen written here, the double bond. This carbon on the right side of the double bond is here with its hydrogen and its methyl group. So this H and this CH3 are actually both attached to this carbon. That's why reading these condensed formulas can be a little confusing, and it's going to take you some practice to go from here to here, but you can do it. But if you draw it like this, then why not just draw it like this? Because this structure here doesn't tell you if this group here and this group here are on the same side or opposite side. So either case is possible. If they're on the same side, again, it's the cis isomer. If they're on opposite sides, trans. We can draw this as a line angle drawing like this. So again, here's my CH3. Here's my CH2. Here's the first carbon of the double bond with its implied hydrogen, not written. Here's the double bond. Here's the other side of the carbon double bond with its implied hydrogen. Here, that might have been in the shadow, sorry. So here's this one, here's that one, and here's the CH3, this right here. That's a cis double bond. Notice it kind of looks like a cup. Both carbons are pointing up or down, doesn't matter. Here's the trans isomer. Follow along, CH3, CH2. Here's the first carbon of the double bond. Here's the double bond. Here's the second carbon with its implied hydrogen here. And the CH3 here. Notice the trans double bond kind of looks like a staircase. The main groups, this guy and this guy, are on opposite sides. This guy here and this guy here are on the same side, so cis-trans. So again, you just got to practice this and stop the video if you have to. Review, stare at it for a while, make models if you can, if you have that ability. But if you have any questions, please send me some messages and I'll be glad to help you. Now you can also have cis-trans isomers without double bonds. How's that possible? You can have cis-trans isomers when you have ring structures. So here's a cyclopentane ring. It's got 5 carbons in it. 5 carbons in the ring, so we call it cyclopentane. But if you have 2 methyl groups on adjacent carbons, you can have 2 possible arrangements. Either the methyl group 1 can be sticking up at you, implied with this wedge that's coming out at you, or you can have 1 going away from you into the tabletop, indicated with this dash. Those are actually on opposite sides of the ring. One's up and one's down. That's a trans relationship, just like this is up and this is down. Same thing here. It's almost like, let's imagine that the ring is here. You're in the plane of the paper, and you're looking at the ring from this direction. What you would see was the ring would be flat, and you'd see a methyl group sticking up here, and on the next carbon it would be down. This is a side view. Side view. So you can see they're on opposite sides. Opposite sides means trans. I hope that's clear. Here in this cycloalkane, you can have a cis isomer where they're either both pointing up or both pointing down. So if you looked from the side, you would either see both methyl groups on adjacent carbons on the same side up, or they'd be pointing down. In either case, they're on the same side. So they're called the cis. Sorry for my sloppy writing there. They're called the cis isomer. So that's a special type of cis-trans isomers that does not involve a double bond. So again, just now you can see why organic chemistry is such a complicated course for people, especially at the beginning. Now let's spend the rest of this video and the next one probably on naming some hydrocarbons. We'll start off with alkanes, saturated hydrocarbons, And then we'll go into alkenes a little bit, and then alkynes and cycloalkanes, and then that will finish up this this part of the course, chapters 12 and 13. So there's some rules you have to follow. Number one, find the longest continuous parent chain, which we'll call the carbon backbone. Number two, you got to number this chain either left to right or right to left based on finding the longest chain. You number the chain closest to the branching. You start at carbon number one would be the one closest to the branching. So I will give you examples of each of these. We'll clarify these. If both ends have branching at the same number of carbons in due to symmetry, then you go to the next substituent to decide. You name each substituent. Now again, substituents are things like this. They're something that's hanging off of the ring. They're something that is not part of the main chain. These methyl groups are substituents. They could be CH3 groups, they could be a bromine atom, they could be a phenyl group, all sorts of things. But you name each of those substituents indicating which carbon it's on, but you use a number. When the same alkyl group is present more than once, you use the prefixes di for 2, tri for 3, tetra for 4. When several different alkyl groups are present, like any of these, there's many molecules that have a mixture of all these present in the same molecule. You list them in alphabetical order. So you look at the first letter of the name. Now, when you use these prefixes, these do not count in alphabetizing them. These are just telling you how many of each substituent there are, or how many of each of these you have. But it does not count in alphabetizing. And I think I have a couple examples, at least one that will show you how that works. Now I want you to memorize these alkyl groups. What do we mean by alkyl group? What I mean is these are based on real hydrocarbons. So let's go back to that slide. Let's go back to this guy here. And notice that the simplest hydrocarbon is methane. Well, if you just cut off one of the hydrogens right there, now you have a carbon with 3 hydrogens, but it's got room for one more bond. So that CH3 can actually be part of a larger molecule. Well, we call that a methyl group. We drop the ANE ending and add a YL and call it a methyl group. If you go to the next hydrocarbon in the series, this one, ethane, if you cut off any of the hydrogens, it doesn't matter in this case because they're all the same. If you cut off this one, for instance, you have 2 carbons in a row, CH3, CH2, and then a single bond that can be attached to something else. We call that a ethyl group. We drop the ANE ending and call that the ethyl group. So you can see here it's CH2, CH3. You take a propane molecule and you cut off. Now you do have a couple different ways of attaching this 3-carbon group to a chain. You can either remove this hydrogen, any of these 3 here, and you get what's called a propyl group. Okay, that's this one. Or if you cut off this one here and now attach this group to a larger chain, you're attaching this 3-carbon substituent at the middle carbon. That's an isomer of that, so we call that isopropyl. See, you're not attaching at the end carbon, but you're attaching at the middle carbon. But notice both these propyl groups have the same numbers of carbons and hydrogens. They're C3H7, C3H7. This is C3H8 because that's an actual molecule of propane. These are not molecules. These are just pieces of a molecule that's part of a larger molecule. But we use the same name as the parent hydrocarbon. We just change the ending to YL. So that's key, though, for you to understand that. And now we'll practice using that. There are many other substituents, but these are some of the common ones. Like you can have the butyl group where there's 4 carbons in a row, the T-butyl group, the isobutyl group. You can have halogens attached. So when chlorine's attached, we change the ending to O, chloro, bromo, fluoro, iodo. You can have a benzene ring attached as a functional group or a substituent. Now it's not called benzyl, it's called phenyl, P-H-E-N-Y-L. But that's benzene itself. But you cut off one hydrogen, and now you have room. This carbon can actually attach. This whole thing can be attached to another longer carbon chain. We call it a phenyl group. So let's run through some examples here. Now, I'm kind of giving you the answers all in one, so I'll just review this with you. So let's say you have this molecule here. Now what I would do if I were you is now you look at it and you try to find the longest chain of carbons. In this case, this is the longest chain. So these beginning examples, I'm going to make the longest chain straight across. But it doesn't have to be. There's a few here that aren't. Notice, no matter how you try to count, 7 is the longest. If you try 1, 2, 3, 4, 5, 6, no, only 6. 1, 2, 3, 4, no good. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, no. 1, 2, 3, 4, 5, 6, 7. There's my longest chain, so I circle it. But now, how do I number it? Do I go 1, 2, 3, 4, 5, 6, 7? Or do I go 1, 2, 3, 4, 5, 6, 7? It does make a difference in this case. In this case, I number this chain left to right. This lists substituents in alphabetical order. So I number them left to right because if I do that, notice what happens. 1, 2. At the third carbon, there's a methyl group. 3-methyl, 3-methyl. At the 4th carbon, there's an ethyl group. So that's 3 and a 4. Remember that. If I start at this end, I get 1, 2, 3, 4. I get 4 ethyl still, but then this one would be a 5, 4, 5. It's always best to give the substituents the lowest combinations of numbers. So 3, 4 is a lower combination of numbers than numbering it this way, which would give me 4, 5. Very important for you to be able to do that. It's a basic skill in naming these hydrocarbons. Then the thing you got to do is name them and list them in alphabetical order. This starts with M, this starts with E, so this one will come first. So even though it has a higher number, it's going to come first in the name, so we list it first. Notice again the number, dash between a number and a letter, the name of the substituent, ethyl, another dash to separate it from this one now, which we're naming. At the 3rd position, there's a methyl group, dash methyl. Now we're done naming everything, so we don't need any more dashes. We just name the longest chain. 7 carbons is heptane. So use dashes between numbers and letters and commas between numbers. It might help to draw it like this. Here's a sort of a combination of a fully expanded Lewis structure and a condensed formula. Same structure, but now it's kind of spread things out so it's a little easier to see. 1, 2, 3 methyl, 4. I have an ethyl group, but I've alphabetized them. Or if you're a chemistry nerd, you like to draw line drawings. So notice here's the line drawing of this compound. Let's see how I did that. So what I did is I just found the longest chain of carbons, 7, and I put it straight across. 1, 2, 3, 4, 5, 6, 7. So then I just, okay, at the 3rd carbon, 1, 2, 3, it doesn't matter if it's pointing up or down. If it's pointing down, and if the zigzag pattern is down, at that carbon that I have something attached to, you draw it straight down. You don't draw it up. This is a mistake to do this, to do that. That is wrong. Don't do that. Draw the methyl group pointing down off the V. So draw it down like that. I see a lot of beginning students doing this. Try not to get in that bad habit. So this comes down. That's that methyl group there. I go to the next carbon, number 4. At that carbon, I have a ethyl group, CH2CH3, which looks like this. That's a CH2. That's a CH3. And then the rest of the chain, 5, 6, 7 here. I can also draw it like this. If I just tilt it a little bit, this is the same as that. So what you need to do is be able to recognize that those are the same. How do you do that? Well, you just take this one and rotate it in some way to get that, or take this and rotate it. How can I make this one into this one? What would I have to do? Here's my longest chain. I'd almost have to, what if I flipped it like that? No, here's my longest chain right here. So it's not as straightforward, but here my longest chain is not in a straight line. It's kind of going like that, which is totally fine. But as long as you follow along with your finger and see that it follows the same branching pattern, it's the same molecule. 1, 2, 3, a branch. 4, another branch. 5, 6, 7. Same molecule. So that takes practice. Let's try another one. Okay, how do we name this guy here? You got to imagine that I'm already kind of giving you the answer here, so you got to imagine that this circle isn't here, so you would try to draw the longest chain. Circle the longest chain. Here again, it's in the horizontal position. 1, 2, 3, 4, 5, 6, 7. 7 carbons in a row. Let's draw it like this. Let's just draw lines between the carbons so we stretch it out a little bit so it's easier to see everything. But this structure is the same as that. So now I would number this one left to right again because this end, these branching points are closer to this end than this end. So carbon 1, carbon 2, carbon 3. At carbon 3 there's a two methyl groups, and then the rest of the chain has nothing on it. So we name that a heptane because it's 7 carbons at the end. At the third carbon there's 2 methyl groups. So it seems redundant, but you have to do this. You not only give the number of each methyl, even though they're on the same one, 3, 3, dash, you also put the word dimethylheptane. You wouldn't call it just 3,3-methylheptane. You indicate that there's 2 of them twice. So seems a little redundant, as I said, but that's the way that they've decided to do it. Notice how I use commas between the numbers, not dashes. Here's the line drawing of this compound. CH3, CH2, third carbon with my 2 methyl groups. CH2, 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 CH3. Hope you're trying to kind of get the hang of this. Now here's a little more challenging one. Here I give you this molecule. Looks kind of like a mess. These are the same molecule, believe it or not. They just look different because I've circled those chains differently. Here I said, okay, I think this is the longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. 1, 2, 3, 4, 5, 6, 7, 8. No, not 9. 1, 2, 3. I'm trying to find the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. Nope. So that's long. But if I look carefully, the longest chain is here. It's hidden, sort of. This is a continuous chain. You can see all the carbons are attached to each other, so that counts. It does not have to be straight across. So pay attention to that when you're doing these examples. So here's my longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's longer than 9. Now, how do I number it, though? Well, I number it like this. So let me just draw this molecule like this, just to show you the carbon framework. Here I have my carbon 1, here's my carbon 2, because at the second carbon numbering this way, I have a branch point here. Anything hanging out of this red circle is a substituent you have to name with a number and a name. So if I numbered from this end, my first branch would not be until 1, 2, 3, 4, 5, until the 6th. And then this would be 7, 8, 9. 6, 7, 8, 9. Nope. This is clearly lower. 1, 2, 3, 4, 5. 2, 5 is better. So at the second carbon, there's a methyl group. M comes before P alphabetically, but it won't always be that way where the number is lower than the number on the left is lower than the one on the right. It doesn't always have to be that way. Did that one example show you that? Yeah, this example showed you that. It doesn't always go alphabetically and sequentially in numbers, low to high. You have a high number, then a lower number. The key here is I'm putting the substituents alphabetically. That's the number one rule to follow. So here's my longest chain, and I've numbered it this way, as you can see. So that's why the final name I come up with is it's based on 10 carbons. So here's my decane. I have a 2-methyl. That's this guy. And at the 5 position, I have a 3-carbon substituent. That's based on propane, so that's called propyl. And then you finally give it that decane name, no dash in between. And here's the line drawing of this. Notice I've drawn this line drawing with the 10 carbons in a row horizontally, just to make it easier to see. But this is the same as that. And I'll leave it up to you to figure that out. But here is carbon 1, carbon 2 with my branch, 3, 4. And then I come to the 5th, that one. And I have a propyl group. So here's the propyl group, 1, 2, 3. And then the 6th carbon, 7, 8, 9, 10. Nothing to do there. So make sure if I give you this, you can go to that. If I give you this, you can go to that. You can figure out the longest chain, you can alphabetize, you can number them properly. These, I would say, are intermediate level problems. This is a somewhat easier problem than this one, because this one, the longest chain was a little bit hidden on you. You can also have hydrocarbons that have a benzene ring on them. Look at this one. This one looks a little strange, maybe. But how would you name this compound? Well, this is not part of the longest chain. You got to find the longest chain of singly bonded carbons. Here it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be based on the hydrocarbon that has 9 carbons, which is nonane. And then you'll kind of work backwards if you want. You number it from right to left. This is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. Why again? Because if I number it this way, my first branch isn't until the 3rd carbon. This branch this way, the first branch is the number 2, a lower number. So I number it this way. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, 7, carbon 8, carbon 9. This numbering is only of the parent chain. So here's my 2-chloro, here's my 5-ethyl, and here at my 7th position I have a phenyl group. Notice this is just coincidence, but the numbers go low to high at the same time as the alphabetizing goes, C before E before P. That's not always the case. And here's the line angle drawing of this. So again, I'll leave that up to you to go from here to here and back and forth. Either way. This one here has a rather funny looking name. 7-cyclopropyl-355-trimethyl-decane. Why is that here? So here's my longest chain. I number it right to left because my branching point would occur here. And I have at this 1, 2 at the 3rd position, I have a methyl. Let's see, 3, 4. At the 5th position, I have 2 methyl groups, so I call that 5,5-dimethyl, indicating not only there's 2 with the numbers, but there's 2 with the prefix for 2 methyl groups. And then at the 7th carbon, I have the cyclopropyl. That's a 3-carbon cycloalkane, so it's a ring of 3 carbons based on propane, propyl. And here's how I'd name it then. I'd alphabetize them. So C comes before M. That's the only 2 substituents I have. Something starting with the letter M and something starting with the letter C. Notice that you think, well, this is the letter T. But remember a couple of videos ago I said that the prefixes for indicating how many there are, di, tri, tetra, that does not count in naming these things. So the M is what counts. So C comes before M. So this is the proper name. 7-cyclopropyl 3,5,5-trimethyldecane. Notice when I say the name, I don't say dash, comma, etc. That's implied that that's there. But you can see all these names have the same format. Dashes and commas used in the same way. So I'm already at 30 minutes on this video, number 4. It's going to take me 5 videos to get through all this. The last video should be somewhat shorter because all that's left is naming some alkenes and alkyne derivatives.